Welcome back. In our previous deep dive, we used a clever whittling trick to build the rule for 11. We learned to chop off the very last digit of your number, subtract it from the entire remaining front section, and check if it is divisible by 11. But here is a beautiful mathematical secret. The number 11 is just the beginning. 11 is really just 10 times 1 plus 1. What happens when we look at 21, 31, or 41? There is an entire hidden family of divisibility rules for any number ending in 1, and the algorithm is breathtakingly simple. Let us define our numbers. Any divisor ending in 1 can be written as 10k plus 1, where k is the tens digit. For 11, our k is 1. For 31, our k is 3. For 61, our k is 6. To check if a massive number is divisible by 10k plus 1, you chop off the last digit, let us call it b, multiply it by your k value, and subtract that from the remaining front section of the number, let us call it a. The formula is simply r equals a minus k times b. If the result r is 0, or a multiple of your divisor, the original number is in the club. Let us prove this algorithm works with a rapid-fire round of 5 examples. Example 1. Divisibility by 21 where k is 2. Let us test the number 357. Our multiplier k is 2. Chop the 7. Multiply by 2 to get 14. Subtract 14 from the remaining 35. 35 minus 14 is 21. Since 21 is obviously a multiple of 21, 357 is perfectly divisible. Example 2. Divisibility by 31, where k is 3. Let us test the number 868. Our multiplier k is 3. Chop the 8. Multiply by 3 to get 24. Subtract 24 from the remaining 86. 86 minus 24 is 62. Since 62 is exactly 31 times 2, 868 is in the club. Example 3. Divisibility by 41 where k is 4. Let us test the number 1189. Our multiplier k is 4. Chop the 9. Multiply by 4 to get 36. Subtract 36 from the remaining 118. 118 minus 36 is 82. 82 is exactly 41 times 2. It works flawlessly. Example 4. Divisibility by 51 where k is 5. Let us test the number 1377. Our multiplier k is 5. Chop the 7. Multiply by 5 to get 35. Subtract 35 from the remaining 137. 137 minus 35 is 102. Since 102 is 51 times 2, 1377 is perfectly divisible by 51. Example 5. Divisibility by 61, where k is 6. Let us test the number 2013. Our multiplier k is 6. Chop the 3. Multiply by 6 to get 18. Subtract 18 from the remaining 201. 201 minus 18 is 183. 183 is exactly 61 times 3. The algorithm never fails. Why does this specific equation detect these multiples every single time? For those who love the absolute certainty of rigorous logic, let us break down the exact mechanics behind this system using two powerful mathematical tools: algebraic substitution and mathematical induction. Let our original generic number be n, which equals 10a plus b. We want to know if n is divisible by our target divisor, 10k plus 1. Let us take the result of our chopping rule, r equals a minus k times b, and multiply the entire expression by 10. 10r equals 10 times the quantity a minus k times b. Distributing that gives us 10r equals 10a minus 10k times b. Now look at our original number equation. N equals 10a plus b. This means we can isolate 10a as n minus b. Let us substitute n minus b into our rule equation. We get 10r equals n minus b minus 10k times b. If we factor out the negative b, we get 10r equals n minus b times the quantity 10k plus 1. Rearranging this to solve for n gives us a beautiful revelation. N equals 10r plus b times the quantity 10k plus 1. Look at that second chunk. It contains our exact divisor. Because that chunk is mathematically guaranteed to be a multiple of 10k plus 1, the divisibility of the entire original number n rests completely on 10r. Now, what does it mean about the divisibility of r? Let us see. You might ask, we proved that 10r must be divisible by 10k plus 1, but our rule only checks r, not 10r. How can we legally drop that factor of 10? This is where one of the most fundamental principles in number theory comes into play: Euclid's lemma and relatively prime numbers. Let us look closely at our divisor, 10k plus 1 and the number 10. Is 10k plus 1 divisible by 2? No, because 10k is always an even number. Adding 1 guarantees that 10k plus 1 is always odd. Is 10k plus 1 divisible by 5? No. Any multiple of 10 ends in a 0, so 10k plus 1 always ends in the digit 1. It can never end in 0 or 5. Since the only prime factors of 10 are 2 and 5, our divisor 10k plus 1 shares no common factors with 10 other than 1. In mathematical terms, they are strictly coprime. According to Euclid's lemma, if a number divides a product 10 times r, and it shares no common factors with 10, it must divide the other part, r. The 10 contributes absolutely nothing to the divisibility by 10k plus 1. That means 10k plus 1 divides 10r, if and only if 10k plus 1 divides r. The two conditions are mathematically equivalent in both directions. Checking the tiny whittled down result, r equals a minus k times b gives you the exact same mathematical truth as testing the massive number n, with zero long division required. If you loved uncovering the hidden mechanics behind these numbers, make sure to hit that subscribe button. If we want to prove this algorithm scales flawlessly for every single multiple in existence, we use induction on the multiple m. Let us prove that for any integer m greater than or equal to 1, the number n equals m times the quantity 10k plus 1 satisfies our chopping rule, the base case. When m equals 1, our number is simply the divisor itself. N equals 10k plus 1. Here, the front part a equals k, and the last digit b equals 1. Applying our rule, r equals a minus k times b means r equals k minus k times 1, which equals 0. Since 0 is a valid multiple of 10k plus 1, the base case falls perfectly. The inductive step. Assume the rule works for some multiple m. Therefore, for our number at step m, our rule yields a front section minus k times the last digit, which is a multiple of 10k plus 1. Now we must prove it works for the very next multiple, m plus 1. To get the next multiple, we add 10k plus 1 to our current number. To find the new digits for the front section and the last digit, we must account for base 10 addition. We have two scenarios. Scenario A, no carryover in the units digit, meaning the last digit is less than 9. The new last digit is simply the old last digit plus 1. The new front section is the old front section plus k. Let us apply our rule to these new digits. We take the new front and subtract k times the new last digit. This gives us the old front plus k, minus k times the quantity old last digit plus 1. Distributing the negative k gives us old front plus k, minus k times old last digit minus k. The k variables perfectly cancel out. We are left with the old front minus k times the old last digit. This is our exact inductive assumption, which we already know is a multiple of 10k plus 1. Scenario B, a carryover in the units digit, meaning the last digit is 9. If the last digit is 9, adding 1 causes a carryover. The new last digit resets to 0, and we carry an extra 1 to the tens place. This makes our new front section the old front section plus k plus 1. Apply the rule. We take the new front and subtract k times the new last digit, which is 0. This simply leaves the old front plus k plus 1. Because our old last digit was 9, our inductive assumption guarantees that the old front minus 9k is a multiple of 10k plus 1. Let us substitute the old front with 9k to see the core multiple. We get 9k plus k plus 1, which perfectly equals 10k plus 1. We generated the exact divisor. The decimal carryover is mathematically absorbed by the algorithm. Through algebra and induction, the logic is absolutely unbreakable. Drop a comment below. What do you think about this divisibility rule? And I will see you in the next movie.